All right, so we're here for the third talk today at MuniHac 2022, and I'm welcoming Michał Gajda. I hope I pronounced the name correctly now. I really trained it. Michał has quite some things to tell you, and he's also working on a lot of things, interesting things. He's also given a lot of talks in the past. So if you, for example, browse through YouTube, you will find talks about Haskell API evolution, also, of course, about complexity. We heard about complexity this morning. So like measuring code quality at large scale. And so I find it personally a very interesting topic. It's really intriguing. Last, he has talked at the Haskell Lab about agile generation of cloud API bindings in Haskell. And yeah, also very interesting, you are a bioinformatician turned fintech practitioner turned Haskell company founder. So yeah, you have worked at Camel Case, at Cross Compass, and then Michał founded the MegaMake company, and he's working in Singapore actually. So you've come quite a long way, and yeah, you've founded the company 5.5 years ago. So yeah, and today Michał is going to talk about a silver bullet for debugging Haskell programs. I'm very curious what that silver bullet would be. So I'm handing over now to Michał. Give a very warm welcome to Michał.
Thank you very much. So today, by the way, my company is now remote, so we all work remotely. It doesn't have to be Singapore, just in case you were interested, right? The question today would be, how do we model debugging? Like as a programmers, right? Maybe we can use these thoughts of how we think and model about debugging to produce kind of meta-level program for ourselves to do it more efficiently, right? To get a better complexity of debugging. So basically, how do we find an error? That will be the first part. Then how do we optimize the time to fix the error? What is the search space that we consider there? And what are our inherent cognitive limits? So we have many different types of errors in Haskell programs. So first, it doesn't compile, kind of obvious. But maybe it compiles up to the moment that it has type errors, right? So it doesn't always crash with the message GHC impossible error, right? Or cannot compile because of missing dependency. It may be more specific thing, just a type error. Or it gives the wrong results. So it compiles, you waited, maybe you have something that compiles for several minutes, and then you get the wrong result. Or maybe performance is too slow. So you are into the time complexity debugging or performance debugging. So you get the right answer, but a day later than you expect, not immediately, right? Sometimes it's a small difference, but usually people are very unhappy with it. Maybe on the higher level, you are using the wrong concept to model the reality. And basically, your program does something very complex when very simple solution would be satisfactory. Like if instead of modeling Slay the Spire, like Gabriela shown, right? Instead of trying to solve the game, you try to learn with AI algorithm, and you get, 2 weeks, it's still playing and it's not winning. Maybe that happens. So depending of the tactic, right? Or maybe user experience is so frustrating that instead of effect of happy user paying for your program and telling other users to do the same, you have the situation when people throw the keyboard at the monitor and ask for their money back. That's also not expected result, right? Or maybe the specification was like in this old drawing, that specification planned for the operating system to work 24/7 and work, but in reality, Windows can only last few days, and then you have some kind of missile cruiser that hangs in the middle of the military training and the high seas, and it needs to be towed back to the shipyard, right, to fix it. So the specification was almost right? They forgot about stability of the operating system. Or even worse example, the specification was actually almost perfectly implemented. It forgot that there needs to be change in the units between feet and meters per second in speed. That this resulted in one space probe that crashed instead of landing in the right place. Okay, maybe it was even meant to crash, but much later and in a different situation, right? So if you look at this order, you have the errors from those that take the shortest time to see, like syntax errors, very quick, or type errors, to some that may take very long time to see and fix. Because if the specification was wrong, maybe you need to re-architect and rewrite the whole module or a whole program. Like the specification that it will work as long as people have at least 1.5 meter height. That's specification for the airbag. Unfortunately, a lot of us have children. They are definitely below 1.5 meter. So basically, airbags ended up, unfortunately, causing deaths of many children that were in the front seat, right? That's the specification error. So basically, we will define the error as difference between what we want and what we actually get. So it can happen at every stage. And not necessarily just coding, right? So we have kind of a read, eval, print loop. But after printing, we check what is the actual result of the program. So we have kind of feedback cycle now. We code, we compile, we see the result. Then we use our eyes or other tools to find the difference between expected and the actual result. And based on this feedback, we fix the program. So how to optimize this process, right? So maybe we can fix errors quicker, right? So basically, we have a difference between actual result and the intended result. And we want to get a difference between the actual program, actual implementation, actual specification, and the intended specification. Between what we actually have and what we want from specification, for example. In particular, Haskell program, right? So basically, we take difference of results and try to compute difference of programs. This is not yet automated. I know it looks like. So we have programs that's called differential programming, or also another word for it is AI or ML training, that compute the difference between inputs from difference in the outputs and optimize it so that inputs, the weights of the neural network, get the right weight, the right values. But for the programs in general, it's pretty difficult, especially if you try to model programs with different concepts and different algorithms. It still needs to be computed in your own head. So the first thing is, since it is your own head, you need to consider limitations of your own brain, right? How many words you can read per second. So you have this program that computes like 1 megabit of logs per second. Obviously, you are not able to read it that fast, right? Maybe if it's just a picture, then maybe you spot some patterns. But you should consider that you have certain number of words per second that you can read. And if your program gives the output in different format, maybe it will be easier or harder to process it at a certain pace. So what we do is usually we use some kind of post-processing. So another program to search for anomalies in the logs. And then we compute the diff of the program, right? So basically, in these terms, we need to spot where is the difference in the output, because a lot of things in the output may be random and may just confuse us, and then compute the difference in the program. And then to compute this difference in the program, we also need to search space of the possible programs that are close to the current one, usually close. So when we start programming as students, we usually have very simple debugging strategies, right? So for example, we have 10 lines and we change one character at a time and hope it compiles. Tell honestly that you never done it. Yeah, I thought so. Okay, so it's been a long time ago. Yeah. If you have a shell program or an assembly, it may be changing one instruction, right? Or one token. And trying to figure out where the problem actually is. So it always happens. If there is no further structure in the program, we are reduced to debugging strategy that is obviously exponential in the size of the program, because you are changing one character at a time and then running it. Yeah. And maybe the only reason the result you get is great achievement, new error message, right? If it's later in the program, that's some hope, but yeah, still not what you want. So this complexity is basically the alphabet that you have to the power of the number of characters. You can change it. Number of tokens that you use in the program times the count of how many times they occur. That may be somewhat hopeful if we have like 50 characters, maybe, with some heuristics, but otherwise this search space is hopeless. So we need to reduce it. And of course, the next thing is that you use tokens. And then, quite few tokens can be a nice recursive functions. We can also change the loops that may go indefinitely into loops that can only go so many times. In the imperative programming, it's while or for, right? But in Haskell, we have mapm and folder and other structure recursion. So I would recommend structure recursion because at least one factor of errors is reduced. Then we can notice that the editor will immediately tell us about some mistakes. So we don't need to spot them. We'll just see them by the change of color. And then we can change the parentheses into the semicolon or something like this. Those that don't know that Haskell sometimes uses semicolons, yes, sometimes it does, in case of case expressions, for example. So instead of semicolon, you may have end of line, basically. Then the next complexity is somewhat reduced, but it's still exponential. And then besides the syntax errors, you have think that compiler gives you the line of syntax error, right? So far I looked at the trivial things, but that sounds very good, because then the complexity is reduced. You know that until this line, probably syntax is correct, right? That said, a lot of programs end with a crash or telling you, oh, I cannot do tail of empty list, which is exactly opposite of this. It doesn't give you the line number where this happened, right? So each time that you try to use function like tail, you may consider using the maybe function instead, and then or pattern matching. And even if you pattern match on the list and you cannot give anything, so you get empty list and you don't know what to do, just write a unique error message, put an error into it, and then you will have unique line number for this problem. That is supposed not to happen, but everything that's supposed not to happen ultimately happens, right? So at least in programming. Then the same thing you can do with the syntax of your error message. You can add the regularity to them. That will allow you to only search in the neighborhood of the line that was given by the error message, right? So then you have a start of the search. Next thing is that you can consider that if lexical analyzer gives you feedback from the editor, then you have much less time. It's below 1 second. If you connect the Haskell language server, that is, by the way, the project here, then you also get a 1 or 2 second delay until you learn about type error, which is much, much quicker than actually compiling the code yourself, right? When you decided that it should be executable now. Then the same thing happens with syntax errors. You can get automatic feedback from the compiler with Haskell language server in shorter time. I would say below 10 seconds, that's very generous. Only if you never used complexity and you don't consider the things that will be discussed in the rest of the talk, which is to reduce the amount of lines in the module. So basically, processing error, if you can reduce time to see the processing error in any way, that will give you a big gain in the time to debug your program. And basically, the worst and the most costly bugs are those that are kind of latent. So if you take 1 month or 1 year or more to fix something, then it may never be fixed. Let's face it. So basically, there is this psychological observation for short-term learning that the speed at which you learn is inversely proportional to the delay you have between your action and seeing the result. So if you think that coding is affected by learning, and the hint is you get better in it with time, so probably it is, then the faster you see the result of anything, the faster you learn, the better coder you become, right? And for those bugs that take longer than you stay in the company, yeah, you never learn, I guess. That's pretty hard. And that's this important number. I can redirect you to the papers later. So decrease latency for any bug. If you can automatically detect the bug by running text tests in the background, that's the next thing you can do, right? So set your editor for automatic running of the unit tests for the modules that you currently run. Most unit testing frameworks, including those for Haskell, have such option. Then we fix the function. So the question is, what is easier to debug, the top one or the bottom one? Yeah. So that who votes for the top one? Maybe this way. And who votes for the bottom one? Okay, so those that voted for the top one, yeah. Can you tell why?
Honestly, for me, it's just a matter of preference. I mean, usually I prefer higher order functions as well, but the way this F is written, where it matches on the one and any other character, is kind of a weird way to define this function, whereas I just spot the error in the upper one quicker.
Yeah, so you read the upper one much quicker than the bottom one. Yeah, so speed of reading is one of the deciding factors. Why do those that voted against vote against? Yeah.
One thing, the way it's written, like the first one, I would write that thing in one line. So like that took me a bit of time because it's not like the common structure of code that I would write code into or find code written with, like just the indentation. I think that's the first thing that I thought of. So like that's why it took me less time for the second one to realize what it does. And I think also the fact that there is higher order functions kind of makes this kind of abstraction that I don't have to focus, like it separates the concept of the list itself and what it's done inside each element, which I think makes it easier. But that may be also biased because of the indentation thing. I don't know.
So that's very important because there are two main messages here, right? The first thing is not just Stack Overflow. We all use templates in our thinking and reading and writing. If it conforms to expected template, it's very hard to find something if it's different. So sometimes we cover it with the template, but generally we read templates that we know much faster. So this is the part that is subjective, right? Depending on the templates we used before, we'll read one or the other faster. But the second message is, as far as we know, if we don't have a template, when we use looping and recursion instead of structure recursion, so instead of higher order function, it's always more harder to debug. So if I express it with unfold there, because it has hidden recursion, it will be even harder, right? Because it doesn't conform to the template. The first conforms to the template. Unfold there usually is not the template that we use. And then on the bottom, we have a loop, right? But we hide it. We always go through the same indices, right? If it's definite loop, it's even easier to debug because the most common error is going looping forever, right? So there are two dominant reasons why we understand our code: how we read it and how we construct it. So basically, if we think about conditions, nested conditions are not recommended. It's better to make a flat list of more conditions than to nest them, because then we need to kind of simulate in our head all the cases anyway. Then nesting of loops is also not recommended. So if you have this kind of recursion, if it's one level of recursion that conforms to our template, it's easy to read. If you would have like 2 or 3 levels of recursion, yeah, how many of you spend time on such functions before rewriting them? Oh, no, nobody. Okay, so yeah, I guess why. Usually people surrender after the third level, and second level is hour versus minute usually. In general, you can talk about cyclomatic complexity as like formalized mathematical measure that measures the same thing. So how many different paths you have in each function that are different. And then, of course, there are dependencies. So supposedly you find a bug that seems to affect the module. How many other modules you need to look through? So this is the typical dependency diagram. This is not the worst one. So we see that most of these modules, you just need to jump a few modules before you come to the end of the program, right? And most of the dependencies that are shared are dependencies of the data structures, like expressions or annotations or module pragma, right? But still, now if you have a problem with path, decide which module you need to fix may be difficult, right? Because there are a few cycles there. So think about this dependency diagram when deciding how much it will take to debug this problem, right? And of course, it may happen that a library function has a bug. It doesn't happen often because usually library functions are used by many more programs. But how long does it does it take to fix it, right? First, you need to check that your actual examples are not buggy. Then you find the difference between the use cases that were previously done and your use case. And then you may need to make a new test that is appropriate for library function instead of using the data from your program. And generally, the rule is that the more users there, it is better. But you can also use one more thing. Check the documentation of this function, right? So is it intended use? Do you use the function that is supposed to count elements of the list to make the list strict, right? Just do you rely on side effect or something that is intended in the implementation and cannot be really optimized or creatively reinterpreted by the person that made the library? Of course, there is this law that tells that every undocumented behavior ultimately will be relied on. That's why you document and you tell this behavior is not supposed to matter, right? Because we will change it in the future. But generally, if you count the interactions between different functions and you make the same kind of dependency graphs for the dependency between functions, it will also tell you how difficult it will be to debug any single function or change it, right? So if there are 100 uses of the same functions that behave in different ways, it's probably something potentially difficult. So for example, this is the nice way of fixing the library. This is bad library, right? A lot of dependencies. You don't want, but it is actually most of the interface. All these modules. This is Haskell SRCX. And this is the library that is easy to use. Why? You have really one data structure, one basic conceptual abstract data structure, and two methods. You read and write to it, right? It's used inside the Shake build system. Basically, it's for caching, so it's basically memoization in this case. And you clearly show the relations between the data structures, right? So you reduce number of dependencies and number of different things that you need to think about when using this code. You can also use things like MuniHac complexity, which is basically number of different operators and operands that they are applied to predict how difficult it will be to debug the program. So if you, for example, use the functions and operands in certain patterns, they will be easier to debug, right? Number of common expressions or high-level type classes, because usually type classes are more complex than straightforward simple functions. Whether you are able to abstract the implementation details or not, right? Because that increases the search space when you search for an error if you have only two functions that you can misuse, right? Versus 20 or 100 functions. You can also decrease the size of the problem, right? Decrease size of each small item that you will test, module or function. And there is also correlation. The bigger modules and functions, the harder they are to debug. You can decrease the latency. So that's why a lot of people start testing and then complain about efficiency, because if it is efficient, then you can test it quickly. You can decrease the latency of tests. And also reduce the interaction. So sometimes you have two modules that do not really need to know each other, right? And that is usually much easier to do by parametricity. So for example, you can replace the data structures that are mutually dependent by two data structures that have the type argument and then merge them later. That's the recommended way to do it in Haskell. You can also reuse abstractions, because basically that means that you write a program that is a new program, but conforms to the interface that you already know, right? So monad interface or monad IO interface. So you don't have a new interface to learn and debug. You can test the type class interface in the same way. So you can actually look at the quick check type classes or HSpec type classes or validity classes for the laws that you can check to check that your monad implementation conforms to the same rules as the others, and then reuse it. And that's the ultimate complexity, because if you look at the number of function interfaces that you need to learn, because you use monads or monad stacks that are like 10 times, then you will see that you reduce your interfaces to almost non-existent, right? You only define new monads, right? And you don't need to relearn the new interface each time. And of course, you can use automatic tools. This is one particle, but there are many others that show you the complexity in your code. So, but it's basically all these tools count some measure, maybe imperfect statistics that correlates with bugs. And usually these measures just tell you that it's harder to understand, harder to read it, right? Things like finding the number of arguments that crosses the limit of human brain, that human brain can normally remember and operate. So depending of the type of exercise you do and how much of the workspace you need, is between 3 and 9 elements that you can remember. So any function that has more than 9 arguments the call cannot be encompassed in a single case. So you should put these shared arguments in the record or something to operate on them separately as a single body. And the same thing for the records and for the type classes. If it has more than this number of functions, it's unlikely that they will be understood in this single iShot, right? And that would be all. I'm still improving this presentation. So if you tell me that it's bad, then I agree. But if you tell me how to fix it and what are the questions and what is unclear, then I will actually fix it. That's a very good point. I should have subdivided the presentation into chapters, and there should be between 3 and 5 chapters, because you need working memory to think about what I'm talking. And then subdivide it, and it is actually known and proven that so conceptually subdivided structures, hierarchies, are easy to understand. Yes, very good point. And no more than 9 modules in a single directory, please. That's true. But the problem is when I search for the best way of picturing things, one of 3 things happens. One thing is that I sometimes get tempted by the pictures that are very nice, that is cut pictures. Then nothing happens. The second thing is that I sometimes draw something that and it visualizes the concept perfectly, but is my own hand draw, and it's not very readable for others. And the third thing sometimes happens, and because I was really thinking how to make it easier, I forgot the third thing. But it's basically the reason. I will try to add more pictures if the cats will not protest or disrupt me this time.
Can you show us something of complexity?
Yes, definitely. Oh, so I think what I would do here, and maybe this. So hope it's a bit more readable. So we can, for example, run a complexity on itself and see. So these spaces are not intended part of the interface now. There is a lot of spaces because I just tried to add one more feature, so the way it displays certain things. And obviously this feature is not interacting well with others. But if we do this, then we run it. It should be slightly better. No, it won't. Because I need to. Okay, so I'm still working on colorizing the output. Obviously, because complexity is often run on the cells, there are not many problems. But you see that it gives you the message with the line and column. And it complains that function spec, which is a test function, has more than 25 lines of code. And it's rather recommended to keep it below 20. So that's, in theory, something that you would spot yourself, but of course, nobody really counts the lines that they're writing. The second is actually not very critical because it's message that it cannot parse one file, so it should be somehow hidden. That's also one bug to fix in this hackathon. But then it also finds type class C that has 5 associated types. I don't know if you would like to try to figure out what type class with 5 associated types does. I do not recommend it for a quick fix of something because it's usually a lot of things tangled. Then it tells that Cabal known extensions is like 102 lines in a single function. So if it's just a case on a single data type, that may be readable, but otherwise 100 lines of different code would be very hard to read. And the type signature of measure all has 6 arguments, should be kept below 5. I think I will reduce them because measure all basically takes what the type of metric that you want to run on a fragment of code base, then type of fragments of code base on which metrics should be computed. So for example, you can count lines of a module and you can also count lines of a function, right? So this is like parametric code there. So there are only 2 types given and 2 arguments. I don't know why 2 more arguments. Probably one on environment would be sufficient. Yes?
Yeah, I also have a question. So first of all, is there some documentation that comes with complexity where I can look up, for example, where you took the numbers from? So when you say like, okay, it should be less than 5, but it has 6, then I mean, very often there is literature on this or somewhere where those heuristics come from. So, and is there some documentation?
So that's an excellent idea. And at the moment, I could write a nascent documentation that would justify, for example, number 6 here, or should be less than 5. It's from these cognitive limits that are documented in the psychological literature or operational memory. The other are basically taken as heuristics from other source analysis software. But there was actually the reason that I didn't document it because I really thought that somebody would join and the person, she or he, would be very interested in statistics of it. And then we could publish a paper about which actual quantities are best thresholds, because usually we can figure it out from basically Git histories what are bug fixes, and where usually they cluster in these functions that cross the thresholds, right? So there is a plan to do it. It's just unfortunately not realized yet.
And a second question, if I may. So is this configurable at the moment? Because, or would you consider making this configurable? Sometimes I have the impression that, well, it's much more than just a linter what you're doing here. But for example, some of the linters that people use are configurable in a certain way, which leads to the problem that you have project A and project B and project C just configuring everything so that they are at least annoyed by their own problems which they have. So sometimes it's actually really good to have a software such as Complexity, which is opinionated and forces that opinion onto people, so that there's not so much room because you are really convinced that you are doing the best.
So the truth is, we have this opinion of the thresholds that were suitable for our projects, and these are the defaults. But everything has to be configured because there is always this one project manager that will refuse to use static analysis tool unless he can or she can increase the limits to be more generous.
Does Complexity support the language server protocol? So can I import it into my editor to directly tell me that I'm writing ugly code?
That's a second time today that this has been requested, along with support for Coverity and similar systems that allow you to visualize this on the code in CI. Either is a great thing to add as enhancement here or anywhere and whenever, but unfortunately it's not yet available. I think that would be the next step. Yeah. I don't know. Should we, for example, check how it works on? Do I have GHC actually? Okay. Okay.
Actually, I liked it very much that you ran Complexity on its own source code because I was going to ask exactly that.
Yeah. So if you run it on a code base like GHC, you not just see a lot of breaches of the threshold. You also see the fragments that are definitely outliers. Like there are functions that I found on recent run that were above 1,000 lines. And the data types that definitely have above 100 constructors, and they are very, very difficult to disentangle and read and fix. And it is a known problem. So if you feel like using the complexity to simplify GHC, I think it's very, very lofty goal because there are a lot of modules in GHC that have very, very narrow people that contribute for this reason, because it's very, very difficult to contribute to a module that is so complex.
One more question, maybe. Have you thought about computing a complexity score or so, like a summary of all the warnings, because some might weigh more than others?
Yes, that's excellent, excellent idea, because especially in case of big projects like DHC, you would see that certain modules, like, I don't know, type class resolution, they are famous for being difficult to fix, but they are also scoring very, very low on any automatic analysis, because basically everything is kind of too big or too untangled. So yes, that would be also a great next step.
Okay. So, well, okay, I'll just take the other microphone. Well, yeah, then thank you very much, Michał. I found this very interesting. I'm very sorry that I had to leave for 2 minutes in between, but yeah, it's really cool, and I hope that you make much progress with Complexity. I'm looking forward to using it. and bragging about my own complexity score on my shirt or whatever. Yeah. So thank you very much, and I hope some of you feel intrigued to join Michał with this endeavor. Yeah, thank you.